In the skies of southern France, an Air New Zealand Airbus A320 is performing several flight tests on a November afternoon. All seems to be going well until suddenly the aircraft starts falling out of the sky while on final approach. What happened here, and what is an Air New Zealand A320 doing in Europe anyway? Let's find out. Welcome to Airspace. On the 27th of November 2008, the pilots of an Airbus A320 in Air New Zealand livery were preparing for departure. The aircraft had previously been operated by a German airline by the name of XL Airways. The airline, however, had not owned the aircraft, but leased it from Air New Zealand for a limited amount of time. In November 2008, its lease ended and it was flown to Perpignan in southern France for maintenance work and repainting. After all this was finished, the pilots of XL Airways were to perform a test flight to ensure all systems functioned normally after all the maintenance work and repainting. If all was successful, they would then fly the aircraft to Frankfurt in Germany to hand it over to Air New Zealand. On the flight deck that day were two German pilots from XL Airways, as well as one pilot from Air New Zealand who was to assist the two Germans during the flight tests. In the cabin, 3 engineers and an Air New Zealand representative travelled with them. Around 4:45 p.m, the A320 departed Perpignan for what was to be a 2.5-hour test flight over western France, followed by a short flight to Frankfurt. 5 minutes after departure, the captain asked air traffic control for clearance to perform an orbit, that is a 360 degrees turn. But his request was denied by the controller with the reason that the flight plan of the flight had no special requests in it, and it should be treated as a normal flight. In busy and congested airspace, such special requests are usually not granted without good reason. Begrudgingly, but without complaining, the crew accepted the denial of their request. The captain was somewhat confused because he had spoken to air traffic control over the phone before the flight to ensure that they would be given clearance to fly maneuvers during their test flight. But due to some misunderstandings, this seemed now not to be the case. Despite all this, the crew continued northwest while climbing to 39,000 feet. This is the highest altitude the A320 is allowed to climb to. Here, where the air is very thin, they tested whether the auxiliary power unit would start up properly. This unit is situated at the tail of the aircraft and is used to provide electrical power and pressurized air to the aircraft when on ground or in the air if certain systems fail. The device successfully managed to start up in the prevailing very thin air and the crew was satisfied. After the check was complete, they requested to return to Perpignan. On the way there, they conducted several tests that did not require clearance by air traffic control. In the end, only one test remained, the so-called low-speed check. The purpose of this test is to check whether the low-speed protection system of the A320 is working correctly. This protection is designed to help pilots avoid a phenomenon called a stall. Stalls typically occur if a plane is pitched up too much, if it's flying too slow, or both. Since a stall will occur at a predefined angle of attack, the A320 is equipped with 3 independent angle of attack probes. These measure the airflow around the aircraft using a vane that is able to rotate depending on the angle of attack. If this angle of attack is becoming too high, the A320's protection systems will do 3 things. First, it will stop the trimming movement of the horizontal stabilizer, which will make a recovery from a nose-high situation easier for the pilots. Second, it will stop the nose-up movement of the aircraft before an actual stall occurs, regardless of how much more nose-up the pilot is commanding. And third, the aircraft will automatically order the engines to maximum power so that the plane will not fall out of the sky due to the speed decay. It is quite an ingenious system that has saved countless situations already. The pilots of XL Airways flight A Tango wanted to check the system on their flight, but had run out of time in the end. By now, they were already on approach back to Perpignan. Let's have a look at how this test is normally done. Usually, it is performed at 14,000 feet, with the third pilot on the backseat briefing the pilots on how to perform the procedure. First, the pilots will bring the engine power to idle and maintain altitude. That way, speed is slowly but surely lost while the aircraft's nose is raised higher and higher in order to maintain the desired altitude. Pilots will then observe the characteristics of the low-speed protection, namely the stop of the nose-up trim movement of the horizontal stabilizer, as well as the automatic engagement of maximum thrust. All this is being done while being very mindful of the absolute minimum speed at which the system must have kicked in the latest. At no time must pilots fly slower than this minimum speed. If they were to do that, a stall and the potential loss of control could occur. While the crew of XL Airways A Tango was en approach to Perpignan, it had already descended well below the 14,000 feet that would have been required for the low-speed test. At this moment, the aircraft was already at 5,000 feet and descending. But at this moment, the captain decided that they would now perform this test anyway. Hastily, the pilot on the third seat proceeded to give the captain instructions on how to perform the procedure, but he did not provide the absolute minimum speed for the maneuver. The captain also didn't ask for it. Meanwhile, the A320 had descended to 3,000 feet or 1,000 meters above the sea, where the captain eventually leveled the aircraft off, reducing engine thrust to idle and started to bleed off speed. The aircraft became slower and slower. Suddenly, vibrations started to shake the aircraft. When it slowed below 100 knots, the stall warning activated.
Stalled, stalled. Stalled, stalled.
This should not have happened since the low-speed protection should have prevented exactly that. Startled, the captain reacted immediately by lowering the nose and applying full power on the engines. Momentarily, he seemed to regain control of the situation after the wings had dipped left and right briefly. But as the engines finally delivered full power and pushed the aircraft to higher and higher speeds, the captain was suddenly unable to control the pitch of the aircraft. The plane raised the nose more and more until it pointed more than 50 degrees up towards the cloudy November sky. The A320 climbed rapidly while its speed reduced to almost zero. The stall warning came on once more. By now, the aircraft was completely uncontrollable. Due to the lack of speed, not enough air streamed over the control surface to make them effective. As the aircraft tumbled towards the ocean, its left wing and the nose dipped down, eventually leading to a situation in which the aircraft regained speed and was once again controllable. The captain started pulling up, but it was too late. The aircraft struck the ocean at high speed, with the nose pointing 40 degrees downwards. It was destroyed immediately, killing all occupants. But why did the low-speed protection not save the aircraft and its occupants? It was precisely designed to do so, after all. To understand this, we need to go back several days and weeks before the crash. After the Airbus A320 had been flown to Perpignan on the 3rd of November, it was due to be repainted. Since the aircraft already carried 2 layers of paint on top of each other, it was decided to remove all this paint before the repaint to save weight. The livery of an Airbus A320 weighs between 100 and 300 kilograms or 220 to 660 pounds. In an industry where every kilo counts, this is substantial. In order to remove the old paint layers, the aircraft was treated with a chemical paint stripper. Unfortunately, the results were suboptimal and the A320's hull had to be sanded thereafter to remove the last bits of paint. This left a dusty residue all over the exterior of the plane. To remove it, the maintenance manual dictates that dry cloths should be used, but this leads to a lot of tedious work. Therefore, technicians decided to remove the dust the easy way by hosing down the aircraft with a pressure washer. This was 3 days before the accident. No protective covers were installed before the rinsing. The aircraft was then repainted and released to service. What nobody noticed was the fact that water had found its way into the probe housings of the angle of attack sensors 1 and 2. When the A320 climbed to cruising altitude to perform the APU check on the 27th of November, the surrounding air became colder and colder. When the plane passed 32,000 feet, it was cold enough that the water inside the probe housings froze, blocking both probes at values around 4 degrees angle of attack. This is a very normal value. Close to the ground, stall occurs at around 15 degrees angle of attack, so 4 degrees is far away from that. When the pilots had completed their tasks, they made their way back to Perpignan, but the 2 angle of attack sensors remained frozen. The logic of the flight control computer works in a way that it continuously compares the sensor values of all 3 angle of attack probes. If one drifts out of range while 2 sensors are showing the same value, the drifting value is rejected as faulty. But here, this logic had the opposite effect. Since the angle of attack probes 1 and 2 froze almost immediately, their values remained the same for the remainder of the flight, while the values of sensor 3 were variable. Therefore, the system rejected sensor 3 as faulty, when in fact, it was the only one working properly. This was not displayed to the pilots. Without knowing that 2 angle of attack probes were frozen, the pilots now started the low speed test. But with the probes unable to provide accurate measurements, the protection systems were unable to fulfill their purpose. Instead, the automatic trim function kept working continuously as the captain lifted the nose higher and higher until the horizontal stabilizer finally reached its mechanical stop. This is a rather extreme position. As the plane became unduly slow, the protection systems should have avoided a stall by limiting any further nose-up movement. But, again, since the probes were frozen, it was unable to detect the high angle of attack. The captain just waited until the moment the protections would kick in, reducing the speed more and more beyond the ultimate minimum speed, which would have been 107 knots. When the speed dropped to 99 knots, the last remaining angle of attack sensor detected that the angle of attack was dangerously high and triggered the stall warning. If you're wondering why the protection system wasn't triggered by the sensor, this was due to the fact that the protection system is not allowed to act on a single measurement, because that could be dangerous for other reasons. For example, a single faulty reading could initiate the protection at an unwanted moment, much like it happened in the 737 MAX accidents. When the stall warning triggered on the XL Airways A320, the captain acted promptly and correctly by lowering the nose and applying full thrust. Now, the airplane picked up speed rapidly, which should have saved the aircraft. But as the plane accelerated, the fully deflected horizontal stabilizer became more and more effective. It produced a huge force that pushed the plane's nose up. Remember, as its movement had not been limited by the protection system, it was fully deflected now. The captain was now unable to counter the nose-up motion, even when commanding full nose-down deflection on the elevators. As the A320 pitched up severely, it stalled once more and became unrecoverable. It crashed just moments later. In the final report, the investigation highlighted many things that went terribly wrong in the making of this accident. First, XL Airways sent its pilots on a test flight, but did not adequately prepare them for the task at hand. Its operations manual did not even describe such test flights, leaving the pilots to improvise. For example, the leasing contract specified a flight test that was to be performed according to the Airbus check procedures, but no such flight check procedures are defined in the Airbus A320 maintenance manual or in the other documents available to operators. When the crew of XL Airways flight A Tango set out to their test flight on the 27th of November, they did not even have a flight plan that would have allowed them to perform test maneuvers. This flight plan should have been filed correctly by the operator, XL Airways. Next, aircraft maintenance procedures were not followed correctly when the aircraft was pressure washed with no installed covers, which led to an ingress of water into the angle of attack probe housings. As the water inside these probe housings froze on flight A Tango, it prevented the probes from moving freely, essentially disabling them and the protection systems connected to them. The crew was not warned of this. Finally, the crew conducted a low-speed test at low altitude while being unprepared. They did not know when to abort the test due to a protection system failure. Had they known that they are under no circumstances to reduce the speed below 107 knots, they would not have reduced it to 99 knots and would not have stalled. In essence, they were probably under the impression that the protection system would kick in anyway. They never spared a thought to the risks and went to cancel the test if the system would not work. This crash is a perfect example for a long chain of unfortunate events that usually leads to accidents. Each corner that is cut reduces safety by a certain amount, until eventually the house of cards falls and an accident happens. I hope you liked my account of this story. If you did, leave a like and subscribe to the channel. Thanks a lot for watching, and see you in the next one.